This is a re-recording of the session from September 30th, 2023, Introduction to C2 Infrastructure for Red Teams. Thank you to everyone that showed up last week. We were very excited to see you there. I am re-recording as promised. Last week we had some audio issues with the recording. I hope this session is useful to you. Please leave comments with requested topics you would like to see covered and explained. Follow us on LinkedIn and YouTube. Share our posts and content with others who might be interested in these topics. Before we begin, I'd like to give a big thank you to Tony Fontana for having us here today. We're stoked to be part of Foxcon's community. Mary for creating our awesome logo and graphic identity and making our convoluted ideas into something beautiful. If you have any graphic needs, please reach out to Dark Cat, Mary Baker Fontana. She's awesome. First, I'll give a little about us intro, then we'll describe the problem C2 is our solution to. We'll touch on the components of a C2 deployment. We'll install and configure an open source C2 and establish a callback from a compromised machine. If you have any questions, add it on the comments. You can reach me on Discord at the handle that will be shared in the next slide. LinkedIn, please connect. Love to meet you, get to know you, see what your challenges are in information security, but also understand what are your goals and how I can help enable them. I'll freely share my experience, and I'm speaking for the other members of Hacker Hermanos when I say that we're really looking forward to connect with you and get to know you. My name is Robert Pimentel, and I work as the lead of offensive security at a Fortune 50 insurance company. I started Hacker Hermanos with my brother Rafael, whose last name is now legally changed to OSCP after passing the exam on the first try. Just go check his LinkedIn if you want to see what I mean. He also passed the CRTO this last week, so congratulations to you, Rafael. I know he has been working very hard for the last 2 years, almost a year and a half, and passed the exams in first try, both on the OSCP and the CRTO. Our hacker Hermana and cloud developer Caitlin Farley, or Evil Pistachio in GitHub and Discord. We combine our powers and love for pen testing, cloud engineering, and red team infrastructure into Hacker Hermanos. If you cannot tell, we're just 3 friends who love IT and speak Spanish. We also love pugs, automation, Brazilian steakhouses, making music, and the show The Office. Speaking of which, we will be releasing a special song made by our very own Rafael, featuring all of us very soon. If you're an Office fan, you might get the reference in the song. And if you like the song, hit Rafael up for a beat. He has worked with professional music producers in Spain. He's very talented and loves music a lot. So he'll certainly help you attain your goals in terms of the song, beat, even alarm, ringtones, etc. Tony Fontana already got one from him. So just check him out. C2 frameworks are the modern solution to a problem that started a while ago. Let's talk about the what, why, and how. So the situation is the following. You compromise the system. You got interactive access to a command interpreter through the network. Eventually, activity like this started being identified as anomalous and detected as a threat. Nowadays, seeing cmd.exe, PowerShell.exe, batch interpreters open a TCP connection outbound is almost a universal indicator of compromise. In 2003, one of the well-known command and control frameworks and suite of exploits was released. This is the Metasploit project. Since then, command and controls have done nothing but continue to evolve. We've seen famous commercial-grade command and control frameworks that have been released in the early 2010s, like CobbleStrike, and more recently, the infamous Brute Ratel. Modern C2 frameworks are still addressing the problem of sending commands to target remotely. That is our what. Why is this necessary, you may ask? Well, when compromising a system with an exploit abusing a vulnerability of some kind, we would want to obtain remote control to do our bidding. C2 frameworks help establish a channel of communications between compromised assets and adversaries. The methods used for this channel of communication are just as important in order not to get caught. Modern frameworks help us blend in with daily activity and evade defenses. What is that bidding I was just talking about? Well, picture this. The Linux server running the Apache application you just ran the exploit against returned what we will refer to as a callback. That is, it connected back to our C2 server. In CTF and training sites, this is often referred to as the reverse shell, where you can run commands and obtain the result of them. You might be interested at this point in downloading the files in that server, bringing your own tools to discover system information and identify opportunities to escalate privileges. You'd want to modify how traffic ingressing and egressing that server behaves. Perhaps you're looking to extend your stay in that machine and move your callback to a different process running in the system. If, on the other hand, you have obtained positive control of an associate's workstation, you may want to capture the keystrokes hoping they'll type in a credential secret. You want to download the contents of their clipboard or even taking a screenshot of their display in hopes of capturing some sensitive data. C2 infrastructure relays commands and the results back and forth from our compromised targets to our C2 server. We know by now that C2 helps us connect to the targets, send commands, receive results, etc. Infrastructure enables the commands to reach the intended targets, and there are several components to this infrastructure that we will touch on in just a moment. For now, let's take a step back and look at the diagram on the right-hand side. We have 3 C2 servers, and between the 3, they're communicating to the target over known network protocols. This is the part where C2 traffic blends in with normal activity like web browsing and DNS. In this diagram, we use 2 common protocols for C2. HTTPS, which is encrypted web traffic, meaning that defenders cannot inspect the contents of the connectivity without intercepting this encryption scheme and analyzing every packet. They'll also need a key. And DNS. It's always DNS, you might have heard if you have been in InfoSec for long enough. It is often not inspected in less mature organizations, and it is virtually everywhere, even your smart TV. Short haul. This is where we run most of our commands from. It has a higher risk of being discovered and blocked because it is connecting to our C2 server very frequently. Long haul, it allows us to establish permanence on the target. We mostly use it to create additional short haul channels that will be used for riskier operations. The callbacks, because of the previous reason, occur over a longer period of time. There's also the consideration of redirection. For this talk, we will not set up a redirector. That is something we will do in an intermediary level session of this version of this session, which is happening on October 15th, 2023. That is Sunday at noon. We really hope to see you there. I'll give you a teaser for now. Redirection of C2 traffic can be done via TCP forwarding, HTTP proxying, content distribution networks, through a mechanism called domain fronting, and a combination of these. When it comes to components of C2 infrastructure, at the core we have 3. The C2 server, this is the backend server that interacts with the target. It controls how the traffic that is sent to and from the target is formatted. It generates implants that connect to the C2 listeners. It modifies the traffic characteristics to blend in with normal network traffic like web browsing and common applications. Tony just showed me a C2 server he set up last week communicating over Discord. Isn't this scary? He's taken it a step further, and now he's writing his own C2, but he told me not to tell anyone this, so consider yourself lucky. C2 redirectors. Think of these as traffic managers. They forward all traffic they receive back to our C2 server while only showing themselves to the target and potentially the defenders. These act as the intermediary and replaceable layer between targets and C2 server. Redirectors allow the attacker to establish new channels of communication if they're discovered without having to create new C2 servers. For this reason, all redirectors are replaceable. Agent or implant, this is the piece of malware that, once executed by the target system, connects back to our redirector and in turn our C2 server. You will still need to figure out a way to deliver the implant to the target system, and for this session, talk, and demo, the initial access portion is out of scope, and we will just copy the payloads into the target's machine file system. Let's briefly discuss some considerations related to operating this deployment securely and reducing liability. Let's also talk about improvements that can be done when working with these deployments in a professional setting. Our C2 server is, air quotes, hidden by the redirector that sits in front of it when talking about inbound traffic. This does not mean, however, that all concerns are addressed and we may not have other issues. Additionally, there's a double-edged sword here depending on your intent. If you work professionally performing red team engagements like I do, you want to take every precaution to prevent the infrastructure you're using from becoming compromised. This could expose your employer or customers to incredible levels of risk and be the end of your consultancy journey. Make sure that errors and omissions insurance policies are up to date. I'll just leave it at that. The concerns we want to address for OPSEC are attribution. You want blue team to have no indicators that this activity is being performed by the red team. Red teams are authorized to emulate or simulate threats, and with that, we take the realism aspect of our operations very seriously. We make sure that everything we do is in our control to look like real threat attackers, and this is the realism aspect. But this does not mean that if we're emulating a criminal group known to use ransomware to coerce their victims into payment, we would run an uncontrolled malware that could potentially damage the customer. This is a critical difference between criminals and authorized offensive security professionals. We avoid causing impact to the business we're helping to protect, audit, assess, however you want to call it. This is where guardrails come into play. These are mechanisms we employ to ensure that our malware only executes in the systems that we're authorized to target. They can be based on the host name of the system, the network the system belongs to, or the domain they're joined as part of. Other operational security considerations include preventing malicious actors from compromising the red team infrastructure. For that, we use strict network controls, preventing anyone not authorized to manage our infrastructure to even have network-level access to it. Deploying, configuring, and securing all of these components on a frequent basis could be a job of its own. These tasks are numerous, complex, and often repetitive, and for this reason, I'm a big fan of automating everything that needs to be repeated consistently. Automation removes opportunities for human error, like forgetting to secure a server within the VPN or configuring a network security group to deny unauthorized access. Automation allows the red team to cut the chase and start attacking the target network without having to spend too much effort on the deployment of the infrastructure required to do so. Some of the solutions we use to deploy resources of this kind include languages like Terraform, and when these resources are created, Ansible is a great solution to configure them. I personally specialize in writing complex deployments of red team infrastructure as code, and I love this discipline and niche of red team work and highly enjoy deploying numerous servers and configuring them with OPSEC considerations we were just talking about a minute ago, already baked in just a couple of commands. If you have a question, please share it in the comments. Ping me on LinkedIn, ping me on Discord. I am very glad to answer those. You can find our LinkedIn, Discord, GitHub. Feel free to take a screenshot of this slide and reach out. Please reach out. We're eagerly looking for your feedback. And please share also the activity and posts that we're posting out. We would like to recruit your help in ensuring that this content reaches folks that are interested in it. I'll share also as a freebie some further reading or talks, articles, videos that you can use to learn about the C2 topic and how it is implemented in the real world. Without further ado, I'll move into the demo in just a moment. So here we have a server running Kali Linux. In this server, we're going to install Mythic, which is a C2, and we'll establish a listener that we'll use to have our target machine connect to it. So the first thing you'll want to do is clone the Mythic GitHub repository into a directory in your file system. You'll also want to make sure you have all of the prerequisite programs installed so that this software can run. Once the repository is cloned, we can change into it and start the build with sudo make. All of these commands are in the repository in the README for the Mythic C2, which is openly available, and you can reference them there. I have prepared them for convenience in a note, and I am just going through the installation so you can see. After the C2 server is installed, you'll need to install the listener profile, which is HTTP, as well as the agent, which is Apollo. Those are the payloads and method of connecting to the C2 from the implant that we'll use today. Once compilation ends, we'll start the Mythic C2 server, as well as the agent that we've installed and the listener profile. Once that is started, we'll also output to the terminal, based on the environment file, the password for Mythic and the user that we'll use. Mythic uses a web interface for console, and that is our attacker console. We'll see that in just a moment. From the build process, what you're seeing on the output is Mythic downloading several dependencies and upstream repositories that are necessary, seem to be in the Go language, for the components in Mythic server to start and generate our payloads, which we'll see in just a moment. After all that is done, Mythic starts creating the different containers because it is a Docker Compose project, and we have the password that we'll use for the web console. So if we move to that web console, okay, okay, now let's proceed to create a listener. But before that, you'll want to open the config inside the C2 profile listener for HTTP that we started during the installation process. And as you can see, we only have configuration for port 80. We'll demonstrate port 443 as well, which is where you can configure an HTTPS listener using TLS encryption. But before that, you'll want to make sure that you have a comma added here. Bear with me. You'll need to have 80, 443. As you can see, the differences. 443 is using SSL, 80 is not. For now, we updated that configuration file. We'll stop the profile. And we will create our HTTP and HTTPS profiles. So we'll call this one 80 HTTP. Mythic listener. And I like to put the IP address that is connecting to for easy references. We want to update the protocol header as well as HTTP. Make sure we're on port 80. And something I tried during experimentation was to turn off all sorts of encryption, but that was not possible. When you turn off the encryption, the Mythic agent does not connect back. So I can show what that encryption looks like on the wire, but for now, let's continue to create the other listener profile. This is for HTTPS. It's the naming convention, Mythic listener. Here we have this as 443. Everything else stays the same, and we can create it. Now, after having created them, we can start the profile, which will in turn start the ports 443 and port 80 to listen on the C2 server machine. We can show that by going to the C2 server machine and querying again for open ports. Here we can see port 80, port 443, and 7443. 7443 being the console where we're seeing Mythic C2 server, 443 and 80 for our HTTP listeners, 7443 for the console, 7443 here, Docker proxy, because please remember this is a container project that has multiple containers. Here we're seeing the Nginx Mythic Web UI. The reason we're not seeing yet the 81 here is because you'll want to have this component of the listener configuration set up. You'd want to stop and start the profile after that is done. Keep in mind we had created a configuration for port 81, the same IP, HTTP. You can do the same for other protocols. It does not matter as long as you have the configuration added inside the HTTP profile here. Okay. If we take a look for open ports, now we can see 81 here. Okay. Now let's move on to the Mythic C2 server and let's generate some payloads. We're going to select the operating system as Windows. We'll select the format as WinExe. We'll add all the commands as to be available in the agent. This agent is going to be the malware running into the machine. And we'll do that first over port 80. As you're seeing here, port 80 is the callback port. Next, and we'll create that as 80 HTTP Apollo exe. Create that payload. Let's create another payload for 81. And let's create another payload for 443. In the meantime, if we go to our payloads page, we can see each of the payloads being created. And if we click on the details, we can see what listener they were created using. So this first payload, 80 HTTP, was created using listener to call back on port 80. We do the same with 81 HTTP was created using callback port for listener on 81. And finally, the 4431 was created using 443 on HTTPS. Okay. All right. Now let's download these payloads into our target file system. Show you the target file system that they were downloaded into. These are our 3 payloads here. I copy them. And let's go to the target machine where we'll execute them. Let's get them here and add them to our desktop inside the payloads folder. Okay, so what I want you to see now is if we go back to our C2 server to show a packet capture of the traffic, if we check the IP address of this machine, we can see that it is 192.168.1.192. We'll go back to our C2 server here. We have a packet capture matching traffic coming on any interface on port 80 TCP and with a IP address of 192.168.1.192 in the header. Whether that is source or destination, that's a different conversation. This filter should match both. So before we move on, I want to show you an example of traffic on the target machine headed inbound to the attacker machine. There currently assign IP addresses to the interfaces in the machine. So with that clear, in the packet capture, okay? If we look at the packets that came in, they're sourced from 192, which is our target machine, with the destination of our attacker machine, which is 166. We'll repeat that one more time. And we can see the traffic coming. Okay. So let's continue on our target machine. The next thing we'll do is going to be running the payload that we had. What I want to show you now is what that payload calling back looks like on the C2 server, and then we'll go to the packet capture and show that as well. So for now, we run payload on port 80. Okay, that payload ran. Let's see our attacker machine to see if we're receiving any of that traffic yet. As expected, we're getting that traffic. This time, the traffic is being originated because of the C2 implant. And we can see in the body of the request a base64 encoded message. If we try to, traffic is periodically being sent to the C2 server. And if we head out to our C2 server, we see a callback. So let's take a look at the event feed. New callback. Let me zoom in case that's not clear. New callback with the process ID 6832. If we go and validate that process ID, we'll find that 6832 is the 80 HTTP Apollo implant. Okay. Furthermore, if we look at netstat, we can see that it has established a connection sourcing from 192, which is our target machine, 192, with a destination of 192.168.166 in port 80 with process ID 6832. This is very interesting because this is our C2 implant that has called back to our C2 server. Okay, we can see that here as well with 6832. Take out the target machine. Okay, if we proceed to interact with this, we can see, let me show you a packet capture from the attacker machine, what it will look like when we change parameters like the sleep, which is the frequency with which the C2 implant connects to the C2 server. If we make that sleep happen every 10 seconds, now this C2 implant will not call back to the C2 server unless 10 seconds have passed. And if we look at the clock here, now we have one callback happen in 13:13:30. The next one will be around 13:13:40 or so. See? Next one in 13:13:50. Next one in 13, 13, 14. Okay, so on and so forth. Now, if we go and interact with the agent that is running on our target machine, let's show some processes that we can see from the implant. So if we look for the process explorer, we can see it with a process ID of 6280. What I want to show you right now is process explorer. Here it is with PID 6280 as we're seeing from the console of the target machine. Okay, if you can see, if you remember here, we have 6280. Other processes we can show are the implant process on 6832. Let's find it here. 6832 is 80 HTTP Apollo. Okay. Something else we can do now is also start our other callbacks on different ports, port 443, port 80, port 81. Do that executing the payloads. We'll have two more payload windows for 443, for 80, in addition to the one that we had running in port 80. Port 80, 81, 443. If we go back to our Mythic console, we can see how we have two new callbacks with PIDs 7684 and 1680. So let's refresh our process list. We said those were 7684. That's 443 HTTPS Apollo. We can see that right here. 7684. 7684. Oop, just had it. 7684 right here. And if we go to our target machine and we query for processes with those names, we see them here. 7684 for 443. 1608 for 81 HTTP. Okay, so now we have our three callbacks, one running on port 80, one running on port 81, one running on port 443. If we look for process numbers, we can see them here, 6832, 1608, 7684. We can see each connected with established TCP connection to port 80, 81, and 443 of the IP address of the C2 server with the source IP of the target machine. Okay, no surprises there. I set the filter to be for Apollo and WinVer. I'm going to zoom this in here so it's easy to read. Bear with me. So you can see I'm filtering for Apollo and WinVer. Okay. But what happens if we run that WinVer command, but we want to use some of the features that the C2 framework brings natively and the agents? We can use something called parent process ID spoofing. This technique was featured on the live session last week, and that's why I want to cover it now. So if we look at the process listing table here, we have a couple columns. We have the column PID and the column PPID, okay? If we look at the Explorer process, which if I remember correctly was 6280, let's find it here. Here it is, 6280. Depending on what is used to execute a program, an attribute called parent process ID will be set in that process information. So let me zoom in here, or actually let's take it to the target machine. The parent process ID here, parent, for the Apollo 443 payload is 6280. Okay, we can validate this going to the Mythic console and finding the Mythic Apollo. agent process. 443 HTTPS Apollo, we see that it has the process ID of 7684 shown in the PID here. But also we can see that the parent process ID is 6280. Okay, this is because it was launched from the Explorer process by just double-clicking it. Okay, Explorer process, we clicked the HTTPS payload, and that took us to having a parent ID for that process as such. Mythic brings functionality that allows you to spoof or change that parent process ID to make activity like this blend in a little bit more. So let's take a look at the PPID parameter. We can provide a parent process ID, right, that we want things to be spoofed under. And in this case, let's select a process ID of like Explorer. So we can see Explorer here. We want to keep an eye on 6280. That is the parent process ID of a new process that we will create called WinVer. If we run WinVer from a command line, we can see the new WinVer process started, and it will appear as a child of PowerShell process, which we have here, 7904. So if we click properties here, we can see that the parent is 7904 for this WinVer process. Now, let's say that we want to execute WinVer with a different parent other than the PowerShell. We want to do that from our C2 implant. We can do so easily with the ppid command. Let's say that we want that to be, as a parent, the Explorer as the parent process ID of our payloads. Let's run Windows Updater as child of 6280, which is the Explorer, as we did earlier. So the takeaway here is you'd want to make sure that whatever parent process ID you're spoofing is going to allow you to create child processes from it. Now, how do we get rid of these processes running in the machine? We can use the task multiple, mark them all, hit exit, and we'll see all of the callbacks dying and not checking back in anymore. This one has not checked in 7 minutes. This is one that we killed way earlier. And we can validate that they're not running anymore in the target machine. Oops, from here. We can do Apollo. None of them are running anymore. Thanks for joining for this session, and we hope it